Hi, so what I'd like to talk about this time out is scientific thought. And so we're going to address a few things here. We're going to look at how science is conducted and just in general. And we're going to look at differences between observations and laws and theories and hypotheses and that kind of thing. And then we'll get towards the end on deductions and causation and correlation. So let's start here by taking a look at this passage here. And here's a passage that comes up in general biology textbooks. Something like this you'll see in a general biology textbook. And so I've highlighted a part in yellow here. And so let's read that. It says, in this section, we will begin by examining how biologists generally follow a standard approach called the scientific method to test their ideas. So there are a couple of things wrong with this kind of statement, and you see this a lot in introductory biology classes, and I wanted to move us away from the idea that is captured in this sentence. I've got two kind of main concerns with this statement. The first one is it says a standard approach. That means that if we went into a center of academic excellence, or a university like CU Denver, that means that everybody would be doing science the same way, and that's just not true. That's not how science works. There are lots of different ways of doing science. You may be mining existing bioinformatics data. You may be making careful observations of animals and plants in their natural environment. You may be setting up experiments in greenhouses. You may be doing statistical analyses on existing data sets. You may be creating complex molecular models and simulations in silico in computers. So there is no standard approach. So if you hear people talking about a standard approach to science, then they understand the process of science a little incorrectly. And following on from that, I have a problem with the word the scientific method. The problem there is with the word the. So I guess is what I would say there is that there is no single scientific method. Using the word the in front of scientific method strongly implies that there's one way of doing things. There is no single scientific method. There are lots of ways by which scientists learn about the natural and the physical world. So we will talk about one approach to doing science, making hypotheses and making predictions, and you'll get into that a lot in lab. And that is one approach to doing science, and it's widely used, but it's not the only approach. So let's dispel that myth that there's one way of doing science and there's one scientific method. So that being said, though, all good science is based on observation. It doesn't matter what kind of science you're doing. You will be making careful observations. It could be observations of the data out of a simulation or observations of simulation running. It could be of insects pollinating flowers and their behaviors during that pollination. It can be the observations that lead up to a hypothesis, but all science is based on careful observation. So as a budding biologist, it's important to start to think about how good your observation skills are. And most people's observation skills, sadly, are lacking. They don't take careful observations. They don't look at the details. They don't think about alternative meanings for what they could be observing. So careful observation. And a lot of scientists use those observations to make hypotheses. Not all scientists, and we'll talk about other ways of doing science in a moment. So what is a hypothesis? A hypothesis is bandied around and people use it a lot. A hypothesis is in its most basic form is just a tentative answer to a well-framed question. And this answer can be falsified. So it's a tentative, falsifiable answer to a well-framed question. So critical here is the question. The hypothesis must follow from the question. So that's a hypothesis, and hypotheses tend to lead to predictions. Predictions anticipate what will happen if the hypothesis is accepted as being truthful. And so this often follows an if-then statement. If the hypothesis is true, then we expect to see the following happen. And so you'll often see if-then statements, but you'll also see other anticipatory statements, predictions, any statement that anticipates the outcome based on the hypotheses. So don't just look for if-then statements, look for language which is synonymous, that means the same as, or very similar to, having the same meaning as if-then statements. So those are predictions. Now, what is the value of a prediction? A prediction lets us anticipate what data we would generate, or what we would see if our hypothesis were truthful. And so when we see that data from an experiment or from a set of observations, we can then give some weight to the truthfulness of our hypothesis. So that's the value of a prediction. And over time, when we've got lots and lots of data that supports a hypothesis, we generate a theory. So we have evolutionary theory, for example. So what exactly is a theory? A theory explains why, explains how something is happening, and it's widely applicable. So evolutionary theory applies to genetic changes that we see under all kinds of different situations. And so far, we've not really found any good examples of when evolutionary theory doesn't hold up. So a theory seeks to explain phenomena we see in the natural world. And here comes Eddie. So Eddie is here saying hello, and he'll go away in a minute. So those are theories, and a lot of people get confused when we're considering theories and laws. So what is a law, and how does it differ from a theory? A law lets us describe what will happen given a certain set of physical constraints. So we could talk here about Newton's laws of gravitation, and so those laws will basically tell us that how two bodies will behave based on their masses and their distances from one another. And so laws basically describe the behaviors that we see under set conditions. If we change those conditions, the law won't necessarily hold up. Now, a theory, on the other hand, a theory is going to be widely applicable, but it doesn't necessarily anticipate exactly what's going to happen under certain circumstances. It seeks to explain and helps understand why and how we see things that we do in the natural and physical worlds. So the last thing I'll say here about theories and laws is that people often say, when does a theory become a law? And people who ask that question don't understand the fundamental role of a theory versus a law. So if we're talking about a theory, then the theory is gonna basically tell us the why, the how, but a law describes what's going to happen under prescribed conditions. So a theory doesn't naturally evolve into a law. So we're not like we have to wait 20 years and then we'll have the law of evolution. Laws and theories do different things, and so we're not necessarily hoping that they will, that a theory will become a law. Okay, so that's all I'm going to talk about in terms of observations, hypotheses, predictions, theories, and laws. Let's talk a little bit more about kind of scientific processes in general. So most of you are probably familiar with the one small step for man, one giant leap for mankind statement made by Neil Armstrong. So when we first went to the moon, we didn't go to the moon with a specific question, a hypothesis in mind. Nobody went to the moon saying, is the moon made of cheese? And then hypothesized that yes, the moon is made of cheese, but now we need to go there and confirm the hypothesis and disprove the hypothesis, I guess, by finding out it's not made of cheese. So what's going on with things like space exploration? That's a form of scientific inquiry, but it's not necessarily question hypothesis based. So that's a form of science called discovery science, and a lot of science is discovery based science. People just do experiments and make observations of the natural and physical world just to see what's happening and what's going on. And that often does lead to hypotheses and predictions, which later give us theories and so on. But there's a lot of science that's done that is just people just trying to find things out by seeing what's going on. So that's called discovery based, and it's one of two general approaches that we can consider science as being done by. The other one we just talked about a little bit, which is called hypothesis-based science. So that's where someone has a specific question, and then they make a hypothesis and then a prediction, and then they usually do an experiment, or they do a field test, or some kind of analyses to to try and disprove their hypotheses. And so that's hypothesis-based science. So those are the two general ways that science can be conducted. And now let's move on to looking at kind of how we interpret the data that we get from our observations, from our discovery-based science observations, or from our hypothesis-based experimentation. And so we'll take a quick look at a common error that's made by all kinds of new novice scientists, and that is mixing up causation and correlation. And so let's take a look at this graph here. So we've got on the y-axis here, we've got what's known as the dependent variable, and that's temperature. And so that's the global average temperature in degrees Celsius. And then down here on the x-axis, that's the independent variable, and that's the number of pirates. Obviously, it's an approximate number. And so we have an independent variable and dependent variable. If you have trouble remembering which is which, the dependent variable usually goes on the x-axis, on the y-axis here, and it's usually what we're measuring. So if we measured, or if we looked back through historical data and we looked at how the number of pirates is decreasing, and that's down here on the x-axis, and you can see these numbers are going down over time. We're plotting them by year. So in 1820 there were about 35,000 pirates, and then they went up a little bit, 45,000 in 1860, but then they went down from then to 2000, when there were apparently 17 pirates. I find that a little hard to believe, probably many more than that, but the general trend is down. And so as the number of pirates has decreased over time, is what we see is that the global average temperature has gone up. And so a common interpretation of this, which when you think about it is very silly, is that a reduction in the number of pirates is responsible for an increase in global climate and global temperature. So what that means is that when pirates go away, when we lose pirates, global temperatures go up. Obviously that's ridiculous. There can be no, how can there be a causation or a causative relationship between number of pirates going down and temperature going up? Obviously there's something else going on here, and so there's what we call a lurking variable. And so coincident with time, which happens to be coincident with the number of pirates going down, global CO2 levels have gone up. And so what's really happening here is that as global CO2 levels have gone up, global average temperature has increased. And so that's the real correlation here, not a decrease in pirates causing the change in global average temperature. So what this graph shows is correlation, not causation. So just because one variable changes, just because we see a variable change on the x-axis and we see a corresponding change in the y-axis, that doesn't mean that one causes the other. And so it's very important not to mix up causation and correlation. So if you see x going up and y going down, for example, that doesn't mean that x causes y to happen. So the way that we can think about that in logic terms, if you like, is that A leads to B or causes B. So that means that if we have A happening, then B will also happen. You may recognize this as a prediction. And so that's a prediction based on causation. If A happens, then B will happen. A causes B. Then no, you can't turn that around. If A then B does not mean that if B then A. So you can't turn those two statements around. So that's a little bit abstract. So let's kind of look at that in a little bit more of an intuitive way. Here's an actual set of causative and correlative relationships. So what you'll see is that in the summer, in the warmer months, temperatures go up, and that causes people to eat ice cream. People go outside, it's nice, people have ice cream, they can be outside, they're enjoying being outside, ice cream tastes good, it cools them down. And so increase in temperatures directly leads to causally leads to an increase in ice cream sales. So if we measured ice cream sales, we'd see that they go up. Also, as the temperature goes up in the summer, burglaries go up. People get burglarized more frequently. And so the increase in temperature during the summer directly leads to an increase in burglaries. And that's because people do things like leave doors open, they leave windows open at night and things like that. So that's a causative relationship. Now we can also draw a correlation here, because sunshine during the summer, temperatures going up during the summer, lead to an increase, cause an increase in ice cream sales, and they also increase burglaries. And so we could say that, well, we see an increase in ice cream sales, then that means that we see an increase in burglaries. Now, obviously, ice cream consumption is not related to burglary. We can't explain the relationship between increased ice cream sales and increased burglaries unless we go back to the causative factor, which is an increased temperature due to the summer coming around. So be very careful you don't mix up causation and correlation when we start looking at data and when we start talking about this causing that. Make sure we're actually saying this causes that versus this correlates with that. What you'll have noticed at this point is that from your textbook reading, from the learning outcomes, there's a lot of other stuff that I don't talk about in these short videos that I make for you guys. So all that other stuff is articulated, it's explained, it's described in the learning outcomes. Now, I could sit here for hours and talk about this stuff, but at the end of the day, you've got to do some of the learning on your own. You've got to get into your textbook, you've got to do some reading, you've got to make notes, you've got to make annotations in your notebooks, you've got to talk to your classmates, you've got to engage with the discussions. So when you look at those learning outcomes, not everything will be covered on these videos. These videos are not enough to get you a good score on the weekly quizzes we're going to do. They're not enough to get you good scores in discussions. You've got to do a lot of other work outside of these short videos. So if you've got questions about what's in the quiz, you didn't talk about it on the video, that's because I'm not going to talk about everything in the videos. Some of it's going to be in the learning outcomes that you're going to see in Canvas. So check those out, and I will see you next time.